Hello, I'm Pascal. Today, I will continue to give lectures in Introduction to Real Analysis. And in this video, we will talk about the densities of a set in real numbers. And maybe all of you familiar with the densities of a set, right? Okay, so let's start together. First, let's start by the definition. The definition of density in real number. So I will talk about any set that is then in real number because we are learning about real analysis. So I just focus on real number. So the definition of density I will give here is something talk about real number. Yeah. Let me say definition. Definition 1.6. Yeah. What is it? A set capital D dense in real number set if every open interval AB contains an element of this where A less than B and A, B are real numbers. Yeah. In other words, we can say that a set G then in real number set if every open interval AB contains at least one element of G, where A less than B and AB are real number. Yeah, this is the definitions of density of a set in real number. Okay, let's start. What set does it then real number? Okay, let me call it theorem. Yeah. Theorem 1.7. What did I say? Rational number set. Yeah, you familiar with this, right? Rational number set. Then this in real number set. Yeah. That is if for every open interval AB where A, B are real number, there exists integer P and Q such that A less than P over Q less than B. Yeah. So rational number set, I mean, sometimes we call rational number, right? Rational numbers than in real numbers. We can say it also. And rational number set than in real number set. So that is to show that rational number than in real number, we have to show that for every interval AB of real number, there exists a rational P over Q such that A less than P over Q less than B. Yeah, in short. And so in this word, it means that there exists integer what? Yeah, integer P and Q such that A less than P over Q less than B. Yeah, we have to find P and Q that is, or that are integer and satisfy the condition. Okay, proof. Yeah, from the theorem 1.5, the theorem that called Archimedean property. You remember? Yeah. From the theorem 1.5, we call it Archimedean property. We take, yeah. Archimedean, yeah. Archimedean property. Let epsilon equal to b minus a, that is bigger than 0 because a less than b, right? And yeah, rho, you take it equal to 1. So from that, you remember, for the Archimedean property, it said like this: if rho is a positive number and epsilon is a positive number, then there exists an integer, or there exists a positive integer such that n times epsilon greater than rho, right? Yeah. So from that, I just replace the value that I choose here. So then there exists integer q, right? You can say q such that from the Archimedean property, let epsilon equal to b minus a and rho equal to 1. So then there exists integer q such that, yeah, q times b minus a bigger than 1. Why? In fact, there exist integer q such that q times epsilon greater than rho, right? And now we replace rho by 1 and epsilon by b minus a. Okay. And from Archimedean property also there is integer j such that j j bigger than qa. Right? Yeah. From Archimedean property also, you remember n times epsilon bigger than rho. And now you just take the epsilon equal to 1. Yeah, epsilon equal to 1 and n equal to j and rho equal to what? qa. So you will get this. You just take epsilon equal to 1, n equal to j, and rho equal to qa in the Archimedean property. So you will get this. Okay? And this from the Archimedean property, this j greater than qa, it is true for a less than equal to 0, obviously. Yeah. Why? Obviously. Yeah. We can call it q is an integer that is positive and j is an integer that is positive. And if a less than 0, so q times a less than 0. So j that is the positive integer must be greater than qa, right? Yeah. And how about for the case where a bigger than 0? Where a bigger than 0? Yeah. I explained you already. For a bigger than or equal to 0, bigger than 0 in Archimedean, Archimedean property, the theorem 1.5 Archimedean property, just take let's n equal to j, epsilon equal to 1, and rho equal to qa, right? Yeah, it's true. And now from this, j greater than qa is true, right? So in this inequality, in this equality, what is equality? In this equality, j bigger than qa, let p be the smallest integer such that p greater than qa. Yeah. Why? The set of the element qa is bounded above by j. Yeah, it is said right here also. And now we will actually find the smallest j, that is j greater than qa or qa less than j. So the smallest j here, I call it p. Yeah, I just take p is the smallest j that is j greater than qa. You got it? Why can I find j here? Yeah, because the set of the element qa, I mean the set that has the element in form qa is boundable by j. So we can find the smallest j such that j less than j is greater than qa or qa less than j, right? So I let p be j that is the smallest one. Satisfy qa less than j, right? Or j greater than qa. I choose p here from j here, but it's the smallest one, j here, right? Okay, and then from this, I will get p minus 1 less than or equal to what? qa. Yeah. By the properties of the supremum of a set. You remember? Yeah. From this, get this. Let me remind you. Beta is sub, right? Of S. So then for epsilon greater than 0, there exists x0 in S such that x0 greater than beta minus epsilon, or we can say like beta minus epsilon less than what? Less than x0. Yeah. Here, from here to here, we get like that. Get it? Yeah. So from this, I can get like p less than what? Less than or equal to qa plus 1. Right? And now I combine these three.